Ladies and gentlemen, my name is Nasir. I'm of the School of Electrical and Electronic Engineering, Cyprus Street. And I'll be making a presentation to you on computational methods in electromagnetics this afternoon. Um, First of all, what is electromagnetism, you may ask? Now, electromagnetism is the study of fields, electromagnetic fields. And what is electromagnetic field? It's a field which exerts a force on a particle, and this particle has a property called charge. Okay, so the study of this force exerted on the particle and also the reciprocal effects of the motion of this particle back on the force is altogether known as electromagnetism. Now, there are different concepts to understand in the field of electromagnetism. There is the fact that the changing magnetic field causes or generates an electric field, and at the same time a changing electric field generates a magnetic field. So the two are sort of interdependent on each other. So, and this is basically the phenomenon behind most of our electrical generators or motors or transformers. The generator, as you may well know, is a device that turns mechanical or chemical energy into electrical energy. Whereas the motor, which is the third image on the slide there, is the converse. It transforms mechanical energy. Mechanical energy into electrical energy into mechanical energy. So as a consequence, it can be used in things like the swinging fan or so many devices actually. All that you require is the turning motion, the torque, which is the rotary motion. And then the transformer just basically converts energy from one form to another. That is the same electrical energy from an undesired form to a better desired form of electrical energy. Thank you. So now electromagnetism also exists, in space, and that is the area in which my research is focused. The electromagnetic spectrum is composed of a number of types of radiation, starting from gamma ray. Actually, there is something beyond gamma ray, but the focus of the electromagnetic spectrum is from the gamma ray to the radio wave. The difference is frequency or wavelength, but they all have the same speed. So now the question is how much electromagnetism? How do you determine how much electromagnetism? The two broad ways are either to take a measurement or to actually determine it by calculation, by knowing some properties of the medium through which it is traveling, and so determining the amount of electric or magnetic field at any point. Now, measurements. In the early days, of course, we didn't have very fast computers, so the only option for determining electromagnetism was by measurement. That's a microwave scanner in the slide there. This is a microwave scanner, and the microwave is a member of the electromagnetic spectrum. So basically, measurements. And the merits or the advantages of measurements is that you're making a direct measurement, and so you're getting a direct result, which is sort of more reliable because it's an instant, real-time thing. And it was a better option in the past when computing resources were not really that good or available. And the advantage is the usually complex instrumentation. Sometimes the instrument can be as huge as a house just to take electromagnetic measurements. So that's the disadvantage. So that brings us to the remember I said computation methods in electromagnetics. So the focus of my research is on computational methods in electromagnetics rather than measurements. So, and it's basically two parts of it, the electromagnetic part and then the computational part. So that's why I have super fast computers here. This is the M12 AI computer. It does trillions of calculations in a second. The University of Manchester has it in the School of Computer Science. So there is a lot of I really didn't want to, bring a lot of abstract stuff because there's a lot of calculus and computation involved, but I really didn't want to put that in. The big picture is what I wanted us to have here. So the advantages of computational electromagnetics is that this offers computers and the potential for doing a lot of billions and trillions of calculations in a few seconds, something that was not possible in the 60s. And there are so many modeling methods, computational modeling methods available, depending on what specific property of the electromagnetic field you are trying to determine. Sometimes your focus is on the frequency, sometimes your focus is on the amplitude. So it also determines the kind of methods you use in doing this calculation. Some methods are very good if you're interested in accuracy. Some are very good if you are just interested in you are not so much interested in accuracy, which means you can beat down the time it takes to get the results. So, but of course the disadvantage is that you have to do that trade-off sometimes, depending on how huge your domain is. For example, there are some calculations like in weather calculations where it involves the entire Earth. Now, when you are doing a calculation that involves the entire Earth, you need to trade off between the time it takes to get the result and the accuracy or precision of the calculation. So basically, in electromagnetic computation, the domain in which you are interested in is divided into grids in space and in time. Well, it's difficult to impute the time aspect of it, but what you need to understand most is that the property of the electromagnetic waves is that there's a rate of change of the particle across space, and there's a rate of change across time, meaning the same particle itself has a sine wave on its own spots across time. So there are three broad methods: the finite difference method and the finite element method, the transmission line matrix method. The finite difference method is where I'm focused on, and there is the explicit and implicit methods. The explicit method is another name for it is the non-stiff method, whereas the implicit is the stiff method. These are some of the areas in which computational electromagnetics, or CEM, has an impact. We have biomedical engineering, physics-based signal processing, we have computer chip design, this up to electronics. RCS is a radar cross-section, and MEMS means micro-electro-mechanical systems. Thank you very much for listening. I know I took too much of the time.